VBT, valence bond theory. Let's try the question. Using valence bond theory, predicts the hybridization and geometry of the following. Complexes, and determine what now? Determine the magnetic properties of each complex. Huh? Nature and property. Yes, I wrote properties. In a way, they should be, but I cannot completely say they're the same. But yes, they could be relative. So, for the following complexes, let's look at one. We're going to look at the exact same thing we just looked at just now. Mn, H2O, 6. There's a reason why I'm using this one. 2 plus. Mn, Cn, 6, 4 minus. Mn, let me use Cr, NH3, 6, 3 plus. Then, which of that is again? Ni, NH3, 6, 3 plus. So I'll try my possible best to solve for all of them, and I'll now give you fresh questions that you solve. Alright, so for valence bond theory, similar to how we did crystal field theory, but it's not the same thing. Are we together? So I'm going to give you 3 steps that we use to deal with this also. So step 1. Step 1 is to first of all identify the metal center. Hey, I've not been on mic. Doesn't matter, Sean. Okay, yeah. First step is to identify the metal center. Are we there? And predicts its electronic configuration. That's the first step. So what's the metal center here now for the first question? We have Mn, H2O, 6, 2 plus. So since it's this, the metal center should be what? Mn. Abi? And Mn is what? 25. Which is argon 4s2 3d5, right? Next step. What's the next step? Calculate the oxidation state. Of the metal. So what will be the oxidation state of Mn here? So that will be Mn plus, since water is neutral, that will be 0 times 6 equals to plus 2. So automatically Mn is equals to what? Plus 2, right? So that means the electronic configuration will change now to Mn2 plus, which is what? Argon 4s0 3d5, right? Next thing you'd want to do, which is step 3, is hybridize. You have to hybridize the what's it called? The metal orbiter with the ligand orbiter. So as to hybridize the metal orbiter and the what? And the ligand orbiter. So this is how we do that. Since we said this is argon 4s0 3d5, no need to write the 4s0 again. here. Observe. So we say Mn, we're hybridizing now. Mn H2O 6 2 plus, right? We still have our argon. Now, how many boxes is in 3D? 5 boxes, right? So you put it down like this: 1, 2, 3, 4, 5. So this is your 3D. You know, if it was crystal field, you say 2 up, 3 down, right? This is 5. Just that we're not doing 2 up, 3 down. Are we together? But we will still apply the method that we used here in this thing now. Are we together? So remember, when we had a weak ligand, that's another thing you take note. We have a weak ligand now, right? When we had a weak ligand, how was the feeling? 1, 2, 3 for a D5, 4, 5, right? Because you have a weak ligand, so that's how you feel it again. You still go 1, 2, 3, 4, 5. If it was a strong ligand, we would have done what? 1, 2, 3, abi 4, 5. Is that not it? So here too, you would have still done 1, 2, 3, 4, 5. If it was a weak ligand, so if it was a strong ligand, but now it's a weak ligand, so we go with the first one, which is the 1, 2, 3, 4, 5. Are we together? Now ligands, they donate lone pair of electron. This is lone pair. You can also represent it as dots like this. You see that it's 2 dots. No, I put 1, it's 2, I put 2. You either represent it like this or like this. If you have a different biro, like if you're using red and blue, as maybe if I had 2 marker now, so I'm using black and I have red, I'll use black to represent the metal electron. I'll use black to represent the metal electron, and I will use red to represent the ligand electron. But now I don't have 2 different markers, so the best thing to do is to use dot to represent it, right? So this is 3D. As you can see, this 3D has already have 5 electrons, meaning that I cannot put 2 again in anywhere here, can I? So what will I do? I'll open the next empty orbital, which is what? 4s0. Are you seeing that? So you open the next empty orbital, which is the 4s0. So this will be your 4s. How many can enter here? 2. Is that not it? Only 2 that can enter here at most. Now when I say lone pair of electron, remember how many lone pair of electron is this guy bringing? 6, Abi. So he's bringing 6 of this stuff. Are we together? It is bringing 6 of this stuff. Please follow me. Ligands donate lone pair of electron. And now they say this guy has 6. So it means he's bringing 6 of this stuff, meaning 6 of this double dot. But this orbital can only take how many? 2, which means it can only take 1 of the lone pair of electrons. So I'm going with 1. That is 1. Are we together? Now 4s is now filled. What do? We open another empty orbital. After s is what? P. So you open 4p. P now gives us ability to put how many there? 6. So how many of this would that be? 3 of this. So we go again. 2, 3, 4. How many of these do we have left? I've already put 1, 2, 3, 4. How many is remaining? It's 2 now. Are we together? Don't get confused. We'll take it again from the top. It's 2. I've already used 4. You still have to put 2 more. You open the next orbital. After S, P. After P is what? D. So that's the 4D. 1, 2, 3, 4, 5. So you now put 1, 2. Are you seeing that? How many of the lone pair? Lone pair now is this. How many lone pair did we put in the S orbital? How many do we put in the P orbital? How many do we put in the D orbital? That's why it's called sp3d2, which is what? Octahedra. sp3d2. Are we together? S1 because only 1 lone pair that we put here. P3 because we put 3 lone pair here. And D2 because we put 2 lone pair here. So that's why it's called sp3d2, and that's what? Octahedra complex. Now look at the question. The question says we should predict the hybridization sp3d2. The geometry, octahedra. Are you seeing that? Then what's the next thing? And then determine the magnetic property. What is this going to be? Is it going to be paramagnetic or diamagnetic? Paramagnetic, because it has 5 unpaired electron. So that's it. 1, 2, 3, 4, 5. 5 unpaired electron. Do you understand? So let's take it again from the beginning. So the first step is to what? Identify the metal center and predict the electronic configuration. So the metal center is Mn. Mn is 25. The electronic configuration is argon 4s2 3d5. Are we there? So now next step, calculate the oxidation state of the metal. Mn plus the ligand here is neutral, so 0 times 6 equals to plus 2. That means you have Mn to be 2 plus, right? Now it's a weak ligand. That's another thing you take note of. It's a weak ligand. So because it's Mn2 plus means it's going to lose 2 electrons, which is 4s0 3d5. Now another way you can write this is argon 3d5 4s0. You can still write 4p0 4d0 because there's nothing in all those ones. You can write it out. Maybe that will help you so that you easily remember. You can also write it out like this. So both of them are allowed. Huh? Oh, thank you. Alright. So you can also write it out like this. So 4s0 3d5, or you write 3d5 4s0 4p0 and 4d0. Now the next is to hybridize the metal orbital and the ligand orbital. Are we there? Now how many lone pair of electrons is the ligand donating? 6 lone pair of electrons, which is this. So we can as well say 12 electrons. Are we there? We can say 12 electrons, but it's 6 lone pair of electrons. So if you want to maybe understand better, you can say 12 electrons. So if you say 12 electrons, you know that it's 6 of this. So 12 of this dots, one dot is 12 of it. So if you check now, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's how you are donating it. But first of all, you fill your metal electron, which is the D5. 1, 2, 3, 4, 5. No space here again. So you go to the next one, the empty orbital, which is the 4s0. You put 2 out of the 12. You go to the 4p, which is the next one. You put 6 out of the remaining, and then the d, you put the remaining 4. But in real sense, you're actually putting 1, 3, and 2 because they are lone pair. So because you put 1 here, you say S1. You put 3 in P, you say P3. And you put 2 in D, you say D2, which makes it sp3 D2 octahedral. Please don't let us be confused. In some videos, you will not see them do something like this. You will not put 1, or sometimes you write it as this. Then you put this, then you put this, then you put this, then you put this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then will now tell you that this is S, this P, and this is D. So SP3, D2. You do this. Some videos will do that. So this is what they're actually trying to tell you in essence. So we have done that. So clean, right, let me clean the board, and we'll do the remaining one. Alright, let's go. Let's go. Uyi, you are around, Abi. Your class is about to start. Your class will start now. It will start. Alright, let's take MnCN6. Please pay very close attention to what I am writing. If you notice, I'm putting box here. And I'm putting Mn here. Then my ligand is inside circle, inside bracket. Then there's something outside here. If that's not how you are writing it in your notes, you will have issues. Oh, I'm telling you, take note of how I'm writing. Don't write anyhow. That's why I was telling the class yesterday that even though all of you are writing like this, if I collect your notes now, it's not what I'm teaching that you're writing. You're writing another thing. So please make sure you're writing what I'm teaching exactly. Before you now come and say, but I attended class. I read. You are reading nonsense. They always remove mark so people know for every nonsense. Alright, can we move? So step 1. It's not playing. Step 1, what's step 1 again? So what's the metal center here? Alright, so we're identifying the metal center, which is Mn, and it's 25, right? The electronic configuration will be argon 4s2 3d. Abi, now let's calculate the oxidation state. So calculating the oxidation state, what would that be? Mn plus Cn is -1, so that's -1 times 6 equals to -4 because -4 is outside here. So Mn minus 6 equals to -4, right? So Mn equals to -4 plus 6 equals to what? So Mn is plus 2, right? Alright, let me use this side. Mn 2 plus means that it's going to lose 2 electrons, right? It will lose 2 from here, and that's it. So we have what? Argon 3d5, or you can say argon 4s0 3d5. But I say you can write it like this, then you now write 4s0 4s0 4p0 4d0. But sometimes you might not get to that d0. So let's see how far. So with that, Mn, let's write our hybridization now. We are hybridizing, oh. Hybridizing. That will be Mn Cn6 4 minus. That will be what? Argon. Then you draw out your boxes. 1, 2, 3, 4, 5. That is the 3D. Because it's a strong ligand, right? The ligand here is strong, right? So we feel 1, 2, 3, 4, 5. That's what we're expected to feel. So let's come here too and do that. 1, 2, 3, 4, 5. As you can see, this 2 is now empty. Are we together? This 2 is empty now. Remember, we are giving it 6 lone pair of electron, which is what? 12 dots or 6 double dots. Are we there? So let's start. 1, 2. What do we open next? The 4s. 3. What do we open next? 4p. 1, 2, 3. 4, 5, 6. What do you observe? It started from this 3D. Abi? The other one that we did started from where? The 4s. And then entered from 3D and did not enter. This one is now a D. How many is here? 2. S 1 and P what? Which is what? Octahedra 2. What's now the difference between this one and the other one? This one is what you call an inner orbital complex. Why is it inner? Because it's starting from the inner 3D orbital. Because why? The ligand electron and the metal electron are sharing the same D orbital. Are you getting it? The metal electron are this one that are standing. These dots are the ligand electron. So the ligand electron and the metal electron are sharing the same 3D. That's why we call it what? Inner orbital octahedral complex. Why the other one that we did? They were not sharing the same D orbital. Instead, it was now in the outer D orbital. So that's why you call that one outer orbital octahedral complex. So now let's check other things. What are we to determine? Magnetic property. Para or di? Para, because it has one unpaired electron. What again then we should look at? The geometry we already said is octahedral. The hybridization is D2sp3. So that's it. I've answered the question. As easy as that. Yes, solve the rest.